Hi, y'all. We're excited to have you here and want to welcome you to Flatiron School's March Madness Bracket Odds with Data Science. My name is Corey Mickelson. I'm the event coordinator here with Flatiron School. So a big part of my job is hosting introductory workshops like today's event to give you the opportunity to meet some of our team and get a better feel of the Flatiron School experience. A quick little reminder, we're using the chat as our main source of communication. So make sure to set that little blue button at the bottom from host and panelist to everyone so we can all chat together. Without further ado, I'd like to introduce our presenter for today, Dr. Brendan Purdy. He is our data science curriculum developer, one of them. So go ahead and take it away, Brendan.
Hey, thank you. Hello, everybody. Thanks for joining. I know, always kind of blows my mind that you get that email or you see the ad like, oh, let's go to a talk online, and you show up. And so that's great. And I'm humbled and thankful for that. Hopefully we've learned something today about something, I guess maybe just about me, but hopefully we learned a little bit about data science, and perhaps we could use that knowledge to help us with our bracket. And I wanted to start out by making sure I don't take myself that seriously. I have a bunch of fancy degrees, but you know, we all need to humble ourselves. So there's 10-year-old Brendan. And I don't mean to brag, but I'm estimating that I was in the top 25% in my small town's youth basketball league. I was power forward. So I have degrees in a bunch of technical fields, including data science, as well as philosophy. I have a background in higher education. And last July, I started working at Flatiron School. And I'm one of the curriculum developers. So what does that mean? Well, we have our delivery team. Those are the ones that do the teaching. And we have the curriculum developers, and we're the ones that write the curriculum that you'll see as a student, whether you're doing the flex at your own pace or you're with a cohort where you're meeting with an instructor. And so we work very closely with the delivery team, and they give us feedback all the time. And one of the great things about a program like Flatiron, unlike traditional schooling, is if something's not working with the curriculum in traditional schooling, it has to go through a whole long process, like at a college or university. Whereas if something's not working for a particular class, we're able to fix it right away, and the next cohort that's coming through, or in fact, for the group that are presently seeing the material, we're able to fix it in, I don't want to say real time, but as close as we're able to. So that's a great thing about our program. We're always updating the curriculum. And so that's what I do. And yeah, I'll keep an eye on the chat if there's any comments. And as you were encouraged, if you want in the chat, make sure you click that little blue button at the bottom left of the chat. And at least on mine is kind of hidden, but switch it to everyone. Otherwise, you'll just be, I think, contacting me. All right, so let's do it. Oh, why did I get asked to do this? Well, obviously the data science bit. But even though I've only been here since July, apparently, even though it's a remote job, apparently I talk about sports all the time. So I've been asked repeatedly to do a whole bunch of stuff on sports. So here we are. So this is our agenda. We'll start talking about the tournament. Right. My assumption here is that we have interest in this talk, but I can't assume anything but rudimentary knowledge about any of it. So we'll talk about the tournament, make sure we understand how that's set up. And then before we get to the algorithm that we'll want to use for our bracket, we need to talk about what machine learning is. And before we talk about machine learning, we talk about data science. So we'll do a high-level overview of what data science is, what machine learning is. And then finally, at the end there, we will have to get a little more specific. We'll still be trying to avoid as much technical verbiage and notation as we can. I'll have 3 slides have a warning at the top that says warning technical slide. And if nothing else, just let it wash on over you. But at a certain point, we did have to get to where we say, hey, this is actually what's going on. But we won't be doing any coding. Won't be showing you any coding. The idea is to understand what these algorithms can do for us. And of course, they're not just used for March Madness, but of course, that's a fun application. All right, so how does the tournament work? And there's a men and women's tournament, and anything, if I say men's, it would work for women's. If I say women's, it works for men. Generally, I'm just trying to be generic and just say the tournament, but there's 2 March Madnesses, so to speak, that run overlapping with each other. So it's called March Madness because there's just a whole bunch of games. There's the round 0 now. So there's an extra 4 teams that started that a few years back, but there's 67 games in a single elimination tournament in 3 weeks. That's a lot of basketball. And the fact that single elimination means there's a lot of excitement. In the first 4 days of the tournament, there's so many games that they overlap and you couldn't even watch them all live at the same time with just watching one game because there's so many games going on. So it's very popular, particularly now with the being able to do this online. There's a lot of individuals who pick their brackets, right? And so we have millions of people every year that do this. At least online, over 40 million people do it, and 70 million are submitted into one of the myriad of contests. And this doesn't even include, right? You do this with your family, the old-fashioned way with paper, or at your work or whatever. So it's probably well over 70 million brackets that are filled out. So it's definitely a cultural phenomenon in the United States to fill out a bracket. And again, feel free to ask questions as we go. So this is also, I doubt you could read this. I can barely read it. But this is what the men's 2022 bracket looked like when it was all filled in with the teams that had made it. And you notice along the top, there's that first 4 that I call it the round 0, the initial play-in games that get you into the official tournament. And so the goal is, right, you pick what team you think is going to win each matchup. And as you go, right, your choices are narrowing and then eventually get to that championship game. All right, so fun fact time, right? We always love the fun facts. 9.2 quintillion. All right, so not even counting those first 4 games, starting at round 0, so that's those 64 teams, right, that we see in the big part in the white. So those 63 games from round 0 to the championship game, that's the number of possibilities there are. So CBS Sports, for example, allows you to submit 6 brackets per email or whatever. So obviously, there's a very small probability, right, that if you're just guessing at random, I mean, essentially a 0 probability that you would get it correctly because there's so many possibilities. Now, just because there's so many possibilities, even if we're not using machine learning, we're going to know that some of them are not going to be rational. For example, a 16 seed, I don't think has ever beat a number 1 seed. And very rarely 15 seed beats a 2 seed and so on down the line. So any sort of those scenarios we could automatically reject, but there's still going to be a lot of possibilities and reasonable possibilities. And where machine learning comes in, it helps us come up with a rational way to choose who's going to win each game. So both UCLA for men and University of Connecticut for women each have 11 national titles. So kind of interesting. That's the most that any one program has won for both men and women is 11. The longest verifiable streak, this was actually just last year, where a single person got 49 games in a row correct. And of course, the question I wonder, well, did he use machine learning or was that just himself? And I don't know the answer to that question. So that's really impressive. And about 45 million Americans last year gambled on March Madness one way or another, and that for a total of $3.1 billion. That's a lot of money. All right, so that is the setup on our March Madness. Any questions there? Well, so can click away that. Okay. Can data science help us with our bracket odds? Can they make them better? And the answer is yes. So let's see how we can get there. So what is data science? And I probably struggled with this particular slide the most, and I've given a lot of presentations or whatever where I define data science. I've yet to be happy with one of my answers, but let's say I'm happy enough for the moment with this one. To discover actionable insights hidden in large data sets by creating models using the tools of mathematics and statistics and machine learning, along with their germane subject matter expertise. So we'll spend a moment or two breaking down this definition. And there it is again up at the top. And so we have the math and statistics part. We have the machine learning, that's where the programming comes in. And then there's the subject matter expertise. Like data is always about something, right? Data is about basketball, right? Data is about image processing. The data is about what movies you watch on Netflix, right? The data is always about something, right? We don't care about data in the abstract. It's meaningless, right? We want data that's about something. That's why data science is a science, because it is fundamentally about the world, right? So these are the three big aspects of what data science is. So let's start with this question. I'm trying to think which one I want to do first. Maybe we'll do this one. Of these three, which one seems most exciting to us? The math and stats, the programming part, or having that specialized knowledge about the subject? Which one? You just throw it in the chat. Which one do you think is the draws you the most to the field of data science? All right, got a machine learning. Thanks for answering. We'll get into some more math stats. So as you're answering, I'll take a moment from not looking, so I'm not just watching each one run in. But I was brought into data science from math and statistics. And I was doing some statistical consulting, and I realized that my programming skills were, well, non-existent. And so I went back to school, got a master's in data science because I wanted to be able to help my customers and my students, as the case was. And I was interested in machine learning, but I didn't have the programming skills to get there. All right, we got machine learning. All right, most of us are saying machine learning, but some math and stats. Cool. And when we're giving definitions like this, we break them into chunks. But the key is that these all form data science. They're all connected to one another, right? It's not like, and sometimes, right, and this happens a lot like in education, where here's the math and stats, here's the machine learning, here's this, right? And you kind of learn them separately. But right, what we want to do, what we do at Flatiron, we try to show you how they work together. So as you're learning about the math and stats, you're learning about why it's important for machine learning, or a better way to put it really, as you're learning the machine learning, you're seeing why the math and statistics are relevant, right? It's, if you're just like, oh, here's the linear algebra, you drop it on your head, you're like, hey, why am I learning this abstract math? I hate this. What does this have to do with data science? And then eventually you can learn machine learning. But the way we do it at Flatiron is that also we have to, have some things we just to say, here's the math. But our goal is, as you're learning the machine learning, we introduce those key mathematical and statistical concepts that help you understand why the algorithms work. Now, I'm afraid I'm going to know the answer here, but I will ask it anyway. Which one scares us the most? And as I ask that, I think I could click to the next guy. Here's a little more detail here. Which one scares us the most? Yeah, math programming, yep. So as someone with a math degree, having taught math, I'm always used to when I tell people that I teach math, they go, oh, yeah, I hate math. I'm like, well, that's great. Thank you for hating my job. Thank you very much for that. So yeah, math, calculus in particular. Yeah, so it's data science is a technical field. There's no way around that. That being said, there's different levels of being a data scientist, just like anything else, right? Like there's a difference between a high school math teacher, community college math teacher, and at a four-year university, right? They're all math teachers. They're all teaching math, but right, there's different levels. In the same way, there's different ways you can be a data science. So say you're getting a master's in data science, you have to, going into the program, say you have to know the calculus and algebra stats and so on. And you do some more of that as you go, of course. But Flatiron, right, we're not assuming that you necessarily know any of this. And so that's why we're teaching you as you go. And you're not taking a whole course on linear algebra, but you're learning the linear algebra that matters for you. And yeah, so the math and the programming, they're both can be difficult. And I certainly, for many, many years, and I was forced as an undergrad to take programming as part of my math major, and I didn't really learn anything. That was part of my own fault. But yeah, I just didn't feel, I never felt comfortable programming. But with the languages, particularly like Python and R, they're I think, a lot more user-friendly than perhaps what we're used to when we think about programming. And a lot of the packages that we use, particularly in Python. So in Flatiron, we teach primarily with Python for our machine learning language. The packages that are used are actually pretty easy. All the syntax are the same or very similar, and it all becomes very familiar, right? As a data scientist, you don't necessarily you're not like creating software on your own. You're not doing a whole bunch of for loops and all that sort of stuff, right? When I think of programming, that's always what I think of. It's more you're using the language as a tool. That's, as a data scientist, you're using the language as a tool. And depending on what you're doing, yeah, maybe you'll be more hardcore programming, maybe less, but primarily data scientists, we're not programmers per se. We need to know the languages well enough in order to use them as a tool to get the actionable results, right? Actionable results means at the end, discover actual insights. What did we learn from the data, right? If we learn nothing, then we try again. But we want to be able to say, hey, this is what we learned from the data. And you can tell your boss, your company, whatever, or you can tell yourself or your bracket, this is what we could do about it. Yeah, and we'll actually mention how calculus, one idea in particular in calculus is a key part of the algorithm we'll end up focusing on at the end. And it's also very used for neural networks, say. So just real quick, so calculus, algebra, stats, and probability. Those are reviewed / taught, depending on where you are, through the curriculum of Flatiron. And again, our emphasis more and more is that you learn the concepts as you need them, so they're relevant, rather than just saying, here is all the math, here's all the stats, and you're like, okay, what am I doing? What does this have to do with machine learning? Again, there's always going to be a case where you just have to have that prologue as the mathematical or statistical prologue. And we'll talk about more, but linear algebra often gives the framework for how the algorithms work. It allows us to describe them mathematically. That's why we need the linear algebra. And the calculus, thanks to our friend the derivative, allows our algorithms know what to do. Calculus tells algorithms what to do. So in our curriculum, primarily we use Python, we use SQL for database, dealing with databases and using SQL and Python together, and we're including more and more SQL. We just had a big curriculum update. We're going to keep on adding more and more SQL because again, as I said, we're able to respond to our students' needs quickly. And so we get feedback like, hey, we need more SQL because you need to know how to deal with databases. We just introduced Tableau officially into our curriculum. It used to be like after the program, you got to learn stuff about it. It's now officially part of the curriculum. Tableau, and it's a software more, and that's where you get your visual dashboards. We all became probably sick of visual dashboards during COVID, right? And they would have the dashboards of hospitalizations and vaccinations and deaths and all that, right? We saw those dashboards where you get a click on things and things move around, right? Tableau is one of the the biggest of those companies. Our studio, you get pretty much everything you could do in Python. With machine learning, you could do in R. R was created more for statistics originally. That's something that you could optionally learn about after the program is over. We have some material on that, self-guided material you could go through. The choice of Python is that in industry, typically Python is used. In academia, R is used. I don't know about more than Python still, but it's used more often in academia. But since we are trying to prepare you for the world of industry and government and whatnot, that's why we focus on Python. Yeah, so a comment here from Barbara. Yeah, so dashboards, they're super helpful, and they're a great way to, and I have this right here, communicating and storytelling with data. So dashboards are a great way for you allow you to do that, and for people actually to kind of play around with the data themselves and get comfortable with it. And again, subject matter expertise is important, and then data ethics and privacy. Also with our new curriculum update, which if you come through Flatiron, you would get. We've had it, but we're adding more and more, and the importance of being responsible with data and being cognizant of privacy is also very important. And of course, if you're a data scientist, you don't necessarily have to be an expert in all these things, but these are at the very least we need to be familiar with. Questions? All right, so what is machine learning? Well, machine learning is a subset of artificial intelligence, right? So we've heard of artificial intelligence. What makes machine learning machine learning? Well, it learns from the data. That's the key. It's learning from the data. So traditionally AI, right? Like they were originally programming AI to play games like checkers and chess and all that. They were just trying to shove in all the rules and go, hey, if the opponent does this, then you do this. And that was very unwieldy, and actually in the end for chess, basically impossible. Whereas if you have enough computational power and the algorithm is able to learn from the data, that's what makes it machine learning, hence the name machine learning. There are two main types of machine learning and three main types of goals of machine learning. We have separate slides on those, so we'll jump over those for a moment. So what are some examples? Also, we have our bracket here. And you could see that there's and these obviously a very small list, but just wanted to give you a taste of some of the other places that we see machine learning. And every day that you use your phone, you search on Google, you watch Netflix, pretty much you're using data science all the time, every day. And we just can't get away with it. And so that's why it is such a growing field, is because it's just used so much. Because we have all this data that's being gathered and we want to be able to learn from it. All right, what about the types of machine learning? Well, they're called supervised and unsupervised, right? So think about, you're watching some kids, right? Supervised means you're watching them. So this is when you say, hey, this is what the data means. Can you then, looking at similar data, can you determine what it is, right? So you're like, hey, this is a cat. You show them another picture. Hey, machine, is this a cat or not? Unsupervised learning is like you go, hey, here's a whole bunch of animals. You tell me how you would group them. So in the first case, you're saying, machine, this is a cat. You show them another picture, cat or not. The other one, you go, hey, here's a bunch of animals. You categorize them for me, and you see what happens. So that's between supervised and unsupervised learning. Questions on that? And just to highlight the last one there, gradient boosting decision trees. That's what we will finally get ourselves down to, hopefully in about 10 minutes or so. And what are the common goals? And this is not exhaustive, but classification and regression. Both of these first two panels, those are types of supervised learning. So classification, and this is a class, there's like these canonical data sets that when you go through data science, everybody learns. And this is about irises, like the flower, and petal length, different parts of the petal. And so in this case, you give it some examples of the irises and their attributes, and then you see how it can classify them. So it's supervised learning, and it groups them. Regression or prediction, which is the type of model that we want to get to because we want to be able to predict, right, our bracket. The most basic example of this is our linear regression model. right? So we have a line that represents the data. And finally, clustering, this is unsupervised. And in this case, we have a bunch of data and we go, hey, machine, we're not supervising you, you're unsupervised. Put the data into clusters for us. And a big place where this is used is with demographic data for companies, right? So you're a member of, I don't know what award programs or whatever they're called, reward programs. But I don't know, you go to Starbucks, right? They have some kind of reward program, I assume. And like they realize you always buy this type of coffee, and they pay a company to do some data mining or whatever, and they find out a whole bunch about the stuff for you. And next thing you know, you have a very specific, tailored to you coupon in your inbox or in your app or whatever. So how did Starbucks know all this? How did they know to target you, right? You're a 30-year-old woman living in a big city, and you are unmarried, and you are making between $40,000 and $50,000 a year. And because of that, they sent you a very specific coupon in the mail or whatever, in your email. Well, they do that by clustering. They get all the information about you, and they tell the machine, hey, go find some clusters for us, right? So maybe that, I don't know, that blue one in the upper left-hand corner is that demographic I just described. But we will be doing the one in the middle, that is prediction. So again, overview, and whenever we're doing overview, making generalizations. So realize that you might go through the program and like, hey, Brendan said that this is true. Well, it is, right? But when you get specifics, then you have to get through the caveats and all that sort of fun stuff. So you might think, well, why am I using data from 2020? Well, data lags from when we could get it. So in a survey, 67% of companies were using ML in 2020. And at that same time, 97% plan to use it in 2021. So it's what all the cool kids are doing, and not just because it's a fad, but because, again, it has results. So we've talked about the bracket. We've talked about data science. We've talked about machine learning. And now we want to finally get to the particular machine learning algorithm that we're going to use. And I just actually saw this morning and I threw it in. Thought it was relatively amusing. We'll talk about decision trees on the next slide because they're form the basis. We're not going to talk about bagging a random forest. They're all very cool and stuff, but interest of time and delving into minutia, we'll just not delving into minutia, we'll just jump over. We'll talk about boosting and gradient boosting kind of at the same time. And then in our last set of slides, we'll talk about the XG boost. So, and it's not exactly this linear. I mean, really, it's more like decision trees, bagging random forests, decision trees, boosting, gradient boosting. It's more of a split, like a tree, like a tree rather than this linear progress. They're kind of like two different species that split off from decision trees. But again, I thought it was kind of amusing. So just don't take the picture too literally. All right, so, and again, we don't have to worry about really what's going on the right. I just want to give a pretty picture of a decision tree. And a decision tree are great because they're so intuitive, right? All right, I need to go to the post office. I need to go to the bank. I need to go lunch, right? Well, you kind of have your brain, okay, well, I could go to the post office first, or I go to the bank first, I could get lunch first, and you kind of go through your mind, okay, which one do I want to do? And and you kind of run through the probabilities. Okay, what will the line be like at the lunch place if I show up at X time versus the bank? What will the traffic be like, right? All these things, how much will I have to drive around town more than I would, right? So we do these sort of decision trees in our brain all the time without even realizing it. And so that's what a decision tree is. It gets the data and it determines the probability of what is the most likely branch. So in this case, there'll be a bunch of, and a few more steps on the line, we'll have a bunch of decision trees that are going to decide who's going to win each game based on the data that's inputted in. So because it's our little underpinning bit here, questions on our decision tree? And they can be used for classification or prediction, but of course we'll be using them for prediction. All right, and I warn you, the next two slides do have our warning about our technical slides. So we will walk through those a little more gingerly, but again, just let them wash over you. So we need to talk about a gradient boosting decision tree, because that's really what we're using. And then the implementation of it in Python and pretty much anywhere else actually at this moment is called XGBoost. So gradient boosting decision tree uses boosting. What's that? Next slide. To create many decision trees iteratively. So whatever this boosting thing means, we create a whole bunch of decision trees. Iteratively means one by one by one by one. That's what this picture is trying to show. It uses weak learning. We'll describe that. But basically, weak learning is we don't care if the decision tree does that good of a job. That's what we mean by weak learning. Strong learning means we'd be very concerned that the tree does a good job. And that's one of the differences between a random forest and our gradient boosting is the random forest, we do want each tree, hence the name forest, because it's a whole bunch of trees. We do want each tree within the forest to do a really good job of learning. And that makes it computationally, takes a lot of computational energy, so to speak, to do random forest, whereas our gradient boosting, because it's just getting a bunch of simple trees, it does not. So it's more efficient algorithm in general. And it does calculate the gradient. And yes, as Barbara pointed out, that is one of the places where our calculus is going to show up. And that gradient, which comes from calculus, allows us to minimize the error for each iteration. The model makes the prediction based on the weighted aggregation of each input. And so let's look at our picture. We have our training data set. We usually split our data set, by which always, but not quite always. But in this scenario, definitely we would. We have our training set and our test set. So we have the training data set, we make a model on it, we test it, and we see, well, we did some of it okay. So then you make a new model based on that, you test again, and we keep on doing it. So this is iterative process. So again, my warning technical slide. And this picture here is the same idea going on. So this is called an ensemble method, and there's a lot of ensemble methods in machine learning. And it's one that combines more than one technique. In this case, boosting is a type of ensemble learning that uses many decision trees. So that's why it's called an ensemble method, right? So ensemble, like a jazz ensemble, you have more than one instrument. And just like when you have a jazz ensemble, right, you have a fuller sound than just a soloist. And so in machine learning, the ensembles often work better than the singular model because they're able to exploit a whole bunch of algorithms at the same time. We talked about what a weak learner is. Well, it does slightly better than chance. Chance means we just would guess a model. This is going to do a little bit better than that. It's going to learn a little bit from the data, but we don't care how good it does for any specific one. But in the aggregate, each time we do this iterative process, it's going to learn a bit better because, as it says on the iterative part, as it learns what it did wrong, the next tree focuses on what it did wrong. The next tree focuses on what that one did wrong. So it's learning from its mistakes bit by bit by bit with these simple decision trees. So, you predict that Kentucky is going to win, and Kentucky doesn't win. Okay, so why not? What features were we looking at? Okay, features by which aspects of the data, and this will continue on until there's some stopping condition as met, and then it aggregates the predictions, and it weights them such that the parts of the data that were harder to learn from are worth more because that means they're more important and they get a bigger say in the final probability of who's going to win the game. Questions? So that's the key idea of how this works. And I have it listed a little bit later, but what are these features, right? So the team's win-loss record, the geography, that is where are they in the country, their conference record. And it gets really into the details. What is the team's field goal percentage? What is their three-point percentage? What is the record of their coach? How have they performed in the tournament in previous years if they've made it, right? So it's a whole bunch of data, and those are called features. How we refer to each individual aspect of the data, the variables, as features. So what's happening at each step in this algorithm, it's picking some features and it sees how it does. And if it did poorly on some of the features, then it focuses on those. Say it didn't do a good job with three-point percentage. So then the next one will focus on three-point percentage. It figures that one out, then it goes, looks at another feature. And we're gonna have, dozens and dozens of features. And of course, that's why we need the computer to do it for us. And this is another technical slide, being mindful of the time. Okay. And this one I'll be probably a little more vague. A residual, and you get these in linear regression, but a residual is how far are you away from your predicted value. Let me go, ooh, a little too far. And now we all have seasickness. If you're old enough like me, then you just had a flashback to using microfiche. And if you don't know what that means, then you are probably born after 1990 or something. I don't know what the cutoff there would be. So the idea of a residual is your vertical distance from the line to the point, right? So from the line to point, that's the difference between the actual value, the black dot, and the blue line, which is our predicted value. That vertical distance there is called a residual. A residual is a fancy way of saying the error. The error is the difference between what we think the data should look like and what it actually is. That's the error, or the residual. Like residual, the leftover part, right? So we can also have residuals in this scenario. You don't have to worry about the specifics of the pictures, but the idea is under each iteration, the first tree, the second tree, the third tree, the residuals, that is the error, that is the distance between the points and the blue curve, are getting smaller. That's the key. We're making the error smaller as we go. And what eventually happens is that the error stops getting smaller in any meaningful sense, right? So it's just converging. It's not going to get any better. And there's ways we could stipulate that. We use a loss function. And actually, we'll see kind of an example. We'll see an example actually of a loss function. And that's what calculates how much error we have using the residuals. So that's the numeric way we find it. So we have a function. The input into the function is the residuals. We have a function. Well, how does the function know how well we are doing? Well, that's when we need to take the second derivative. And by we, I mean the algorithm does it for us. And so there are parts of data science. As long as we have a general idea of what is meant by second derivative, we don't need to be computing them like we do in a Calc 1 class. But if we have an understanding of what a derivative is and what a visual representation of the second derivative is telling us, then we could grasp onto what is meant by gradient descent. We don't have to be an expert in calculus. We don't even have to really claim we know calculus. But if we get that snapshot of what is meant by a derivative and how it apply in this scenario, then we're good to go. And so the gradient descent is where the calculus explicitly comes in, because that's when we're taking the derivative, and that's what's measuring how well we are doing. So those these are all tied together. The residual fitting is the input into the function. The loss function is the function itself. And then the gradient descent is the second derivative of the function. So again, technical slide. It's okay if you just let it wash over you. All right, questions there. And the last technical slide, I tell you basically to ignore unless you don't want to. But this is the heart of the theory of what's going on. So for each tree, we're seeing how far is the tree away from reality. That's residual fitting. We put that into the function. we take the derivative, we get the error, and then we continue on. So how do we implement this gradient boosting decision tree? Well, that's using XGBoost. All right, so we have our data, and I talked about this a couple of slides back. You have the historical seeding in the tournament, the performance, season, postseason, both conference and the tournament, box scores, geography, the coaches, and websites like 538 and others also have their rankings of all the teams. And that is also data you can use. Typically, I always want to say, I always start saying the word annoying. That never sounds good. So challenging. Of the most challenging aspect of machine learning is bringing all this data together, right? I mean, you have like 12, 14 different data sets, and you need to join them, get them all together, and make them so they match and that the variables or the features are in their proper form so you could use your algorithm. I have a question about XGBoost and SaberMax. I will answer that in a moment. So this is called pre-processing and feature engineering. Pre-processing is the stuff you do to prep the data, and then feature engineering is when you focus on those variables that you want to deal with. Once you do that, you could use XGBoost, and that's the most commonly used library for a gradient boosting decision tree. So everybody uses XGBoost. I mean, literally. So it's in if you Google it, you'll see on their official site, I don't know, like 20 different languages at least that use it. Python, of course, and R. And getting back to, again, data science is a science, right? For one, we're using data of the world, right? Right above, we're using data. We're investigating the world. That's a science. And the other part that makes it a science, just like when you're modeling something in chemistry or in physics, when we have our model, right? I mean, anyone could just get a XGBoost, and run it and go, yay, I won. Well, no. It has, they're called parameters. There's aspects of it you could change, and it's called tuning. So that's how is my XGBoost model going to be better or worse than someone else's if we're using the exact same data set and we're doing the exact same pre-processing and feature engineering? Well, that comes down to the choices of how we modify the parameters of XGBoost. So even if we all have the same data and we all have the exact same pre-process and feature engineering, how are we still going to differ in what comes out? Well, that's because it's how we modify or tune the XGBoost function. And so what pops out at the end? And I see I have about 10 minutes. So it's a single elimination tournament. There are 68 teams, if you include that first 4. So it's 68 times 67 because you don't play yourself. You divide it by 2 because, well, UCLA playing Duke is the same as Duke playing UCLA, right? I mean, you don't need to count both of them. So divide by 2. So we get a total of 2,278 matchups. So what pops out from your XGBoost is you get 2,278 predictions. Those are all the possible ways that those 64 teams can play each other. Obviously, they're not all going to play each other. So as you go through your bracket, you would see for that particular matchup who would win, and that is a little tedious. So what does that look like? So this says for the 2021, the one that comes first is, in this case, 1101 has only a 2.7% chance of beating team 1104, and I neglected to look up and remember which those teams were, but whatever teams they were. But based on this, I'm assuming 1101 is not particularly good because they seem to be losing to most teams, and pretty terribly because they have very small probabilities of winning. And I'll come back to the sabermetrics while time for that. But we're almost at the end. All right, so how do you measure success? Well, one measure of success is you beat your friends or your family or your office pool, right? That's maybe the most important one at all. But bracket challenges, and of course you could do this for your office pool, and that's probably similar to how it would be done. So CBS Sports, ESPN or whatever, they usually give you some sort of value. And this is CBS's. I think they're all basically the same. So for every first round game you get right, you get 1 point. Every second round game, you get 2 points. Sweet 16, 4 points, and on down the line, right? And whoever has the biggest number at the end, you win, because you got more picks right, and it's weighting higher. The further you go in the bracket, you're getting a bigger payoff. Now for ML competitions like there's on Kaggle, and if you have not gone to Kaggle, it's exactly what Kaggle.com. It's owned by Alphabet/Google for the record, but it's free. And they have a lot of competitions for machine learning. Actually, it's the #1 machine learning / data science website, in particular for competitions. And so they'll use a metric like log loss. And what they're looking at is how good were your predictions? So who did you predict were going to win, and who did actually win, right? Once the tournament happens. And one thing that's interesting about that is that you get a major penalty from this function if you are really confident, like, oh, I think this team's going to win with 97% probability, and they lose. The log loss function is going to punish you because you were really confident and you were really, really wrong. So if your probabilities are haywire in one direction or the other, and your prediction is wrong, I mean, they're extreme, I should say, not haywire. If your predictions are extreme one way or the other, and that team ends up losing, that you were super confident was going to win, at least your model was, then the log loss function will punish you. So it's still like a weighted system, but it's a more sophisticated bit. And it says ignore the slide unless you don't want to. But this is what that log loss function would look like. I'm not going to even talk about it, but I felt guilty mentioning it, but not showing it. But now I feel guilty showing it and not talking about it. So here we go. So 8 minutes. Oh, awesome. So what's the epilogue here, or the next bit? So I'm doing a write-up for the Flatiron School blog, which you can see right there, simple enough. So also could start, my model could, based on historical data, could start already be set up. But the new data is released in a couple of weeks. That is for the 2023 bracket. I will run my predictions, and I will do a write-up on what my predictions are. And the first round begins on 3/16. And about a month later, after the tournament's over, I'll tell you all how I did. I will also have my fan bracket, because I mean, the ML bracket's cool because you're using data science, but the fan bracket's fun, right? Because you get to be biased and subjective. And I went to UCLA, and they were actually really good again this year. So I'm already picking them to go all the way, even if my machine learning algorithm says they're going on the Sweet 16. I don't care. I have them winning the championship. So the ML is great, but it's also fun to have your subjective bracket and root for the team with your favorite that has a cool sounding mascot and have them go far, or the city you were born in or something. All right, so I'll put up my last slide. I'll ask a question. So sabermetrics. Oh, that slide like makes my face all red. That's cool. So sabermetrics is just using analytics, quote unquote, for baseball in particular. So initially it was just using, I shouldn't say just, but just using statistical methods. In particular, the idea there, Bill James was the main guy, but trying to find new descriptive statistics that better represented what's actually going on in the baseball field. So you definitely think of sabermetrics as a precursor to a modern sports analytics, which uses neural networks, which uses our XGBoost here. So like when you're watching football, I watch tons of football, right? And NFL, brought to you by AWS Cloud and all that. And they're showing you the cool thing and all those probabilities. Those are coming from neural networks generally. So sabermetrics was like the pre-machine learning. But it was the first time where people got serious about trying to be objective about the sport, take emotion out of it, and say, what are the numbers telling us? And the big thing they realized that they didn't have the right tools. So they created new tools, that is new statistics in that case. And that's the same thing that happens in machine learning, data science overall, whether it's sports or anything else, is you reach a problem, and if there's not the tools, then you try something else. And that's why we got this particular algorithm, is because random forests were working, but they weren't working quite as well as they were supposed to. So that's why there was this modification on how we can start at descending trees and get there. Any books on learning Python that you'd recommend? That's Yeah, actually, Kaggle itself actually is a pretty good place to start. The O'Reilly books they're a big publisher of technical books. They're generally very good, but I think don't start with like doing the for loops, the traditional let's learn how to program sort of thing, because yeah, you have to occasionally do some of that, and again, depends what you're doing as a data scientist. But the main thing you need to learn is, here is in scikit-learn, which is the big data science library from Google that is used for like 85% of the things in Python. Do I know how to put in the parameters? Do I know how to make the predictions, bring in the data? So it's that essential data science tools that we really need. And so to that end, I'll remember that question. And when I do post my blog, or when they post for me, the blog post in about 3 weeks from now, I will have a comment about some suggestions for books other than O'Reilly. And just so you realize, O'Reilly, kind of like the auto parts, but not the auto parts, but it's spelled the same way. So O'Reilly is my go-to still for basic thing. And I should add, as a Flatiron student, you have access to all of O'Reilly's resources. There's a plug. Gotta keep the marketing people happy.
If you think of any extra ones, we can add them to one of the slides in your deck, and I can share that with everybody that attended today. Did anybody have any other questions? I did drop a link to schedule a chat with admissions if you guys do have any questions regarding the data science program, and a link to our YouTube channel. That is where all of these videos will be uploaded to after they are sent to all of the attendees.
And thanks again for your time. And hopefully we learned about what data science can do for a very fun application. And you can see then how it could work for other applications in industry and elsewhere.
There is a question in the Q&A that says, are beginners in this field supposed to be concerned about reproducibility?
Oh, you mean this statistical issue of someone be able to reproducing your results? Is that the question? Is that what the question is referring to?
I'm not sure.
Yeah, reproducibility. Okay, so wow, my brain was ready to shut down. You hit me with a deep one. So in the sciences, there is a crisis, if you will, of being able to reproduce results, right? So you do your experiment on your rats and you give them cancer and you give some medicine, some other medicine, and you see in the poor rats, they're dying for us. And right. And then you read that paper and you're a biologist as well, and you read the paper, you try to replicate it and you can't reproduce the results. So yeah, that's a big problem to cite. Now in data science, it's not as big of an issue because in the sense you have your code, right? And of course you should document your code. You have the data. So, and everything is going to be in your code, like how you manipulated the data to get it in the way it is, what you did. So anybody should then, if you sent them the code, they should be able to reproduce that on their own machine, no problems whatsoever. So you can't ship, you can't resurrect the mice and ship the mice to the person, right? And ship your lab equipment and all that. It's not going to work. Whereas in data science, we literally have generally that Python notebook that has everything there, and you can make access to your data. Then someone would be able to reproduce it. And in fact, I mean, whether it's Flatiron or anyone else, as you're learning data science, you'll be given code and basically our exercises, and you'll be reproducing it, the problem, and then you'll be able to do your own tweaks on how you like to do your comments and how you write your code. But you'll spend a lot of time doing stuff that other people will already know how to do. But yeah, so unlike the sciences, other sciences, the natural sciences say, well, that is a big issue. It's not an issue here because if they have access to your data and they have your Python notebook, then they should be able to do it on their machine and they should get the exact same thing popping out. Is machine learning with different models making, yeah, so more specifically about the other models. So obviously different models are going to have different sorts of results. And that is another thing which I didn't mention that is another goal of machine learning is called model selection. And it is nice when things sound like what they are. Model selection means how do you select the best such model? So you have this model here, you have this model here. They're both doing a pretty good job. How do you determine which one is better? And there's suggestions on how to do that. And that's again where this is a science. There's not a one answer to which model is better. You have to decide which one you think is best and offer justification for it. What are the variables was able to predict weight higher? Is it possible that? Ooh, okay. So specifically, and then for James's question, I believe it was stated by Corey that within 3 days she'll email out the recording. Yeah, so within 3 days, the link to YouTube. So Barbara, another good question. What variables are most difficult to predict? I don't remember that offhand, and my excuse is, it's like 30 different variables, right? And so it's for an individual decision tree, that like simple tree I showed you, it's easy to see which variables it likes and which ones it doesn't. But when you have tree after tree after tree after tree, looking at subsections of all the features, then it's kind of hard to wrap your mind around it. And then you get that nice happy prediction. But that gets to another important point, which is called model interpretability. And that's another, it's like your plant. That's another thing we just added in our new version of our curriculum. We just are launching in this month, yeah, March. And so something pops out at the end and you go, oh, okay, I'm going to pick UCLA to beat Duke, not just because I like UCLA better, but because my model tells me. But then someone goes, well, why? Why did your model tell you that? What was going on? And so that's trying to interpret what the model was doing. And so that's exactly that sort of question, what is getting at. So yeah, that you'd actually have to look and see what features it is deeming to be the most important, which ones it ends up ignoring. And then the thing that often happens that surprises us is the traditional features we cared about, like in baseball in particular, going back to the sabermetrics, like ERA, for actually really seeing how a pitcher is doing, ERA is pretty much useless. There's other metrics, statistics that do better. And so that's what investigating these things scientifically does for us. It allows us to actually separate what is truly important versus what we may have just naively thought was important because it was easy to calculate the ERA. If a variable becomes less predictable in the next round of variation, would the model drop less? If it is not helping toward the prediction, yeah, it's going to start ignoring it. It's going to say, yeah, okay, that we're good. We're checking that one off. And it's going to start, and it will continue to focus on those it's having a hard time getting right. So yeah, as it hits the features that it figures out, it's just going to say, cool, we got that. But what are these ones that we're having trouble figuring out? And those are the ones that the algorithm gives them more points for, so to speak. So the ones that it figures out easily, it doesn't get much, the weak learner doesn't get much credit. So where a weak learner is barely doing better than guessing. So if it figures one out and it's barely doing better than guessing, that feature is going to basically be ignored by the model. But it's those features that it can't really say the free throw percentage, right? And it can't really figure it out. It's when one of those decision trees iteratively finally gets it, that tree is going to get a lot of credit for figuring it out. So one feature, though, that is unsurprisingly one that usually is a good predictor is being ahead at halftime. Okay, that kind of makes sense, right? But also the margin being ahead at halftime. But merely being ahead at halftime is a good predictor, which isn't surprising. But we know there's got to be more to it than just that. Really good question. Thank you. That means you guys were listening. You know, it's hard to tell when I'm talking to myself. It's like when I'm talking to my kids, I'm like, well, they're here. I assume they're listening, but I have no way to tell. So I'm glad you guys are responding. That's awesome.
Looks like there's one more question.
Machine learning used a lot in sports industry. Yes, it is. It used to not be because we didn't have the technology. So I don't know how I watch probably way too well. I think I watch a good amount of sports. My wife thinks I watch too much, but so for example, to pick an example, in the olden days, as one of my kids says, anything before he was born was the olden days. So in the olden days, in the NFL and in college, but NFL in particular, football, it was fourth and short, pretty much anywhere on the field besides maybe getting really close to the goal line. And then they probably still do a field goal. The coaches would probably hardly ever go for a fourth and short. Instead, they would either punt it or go for the field goal. Because of machine learning, because of sports analytics, which is saying using data science in sports, pretty much whenever you hear the word analytics now, business analytics or sports analytics, that's just data science applied to that particular field. Is now because of the analytics, and this really started a lot with the Patriots, actually, Bill Belichick and his team, as in the people he works with, not like the literal football players on the field, but the front office guys, is to use statistics to say, hey, what if we go for the fourth and short and we get it, our probability of winning the game just increased. So if we don't go for it, we're more likely to lose the game. But if we go for it and we get it, we're more likely to win. And so those sort of probabilities, conditional probabilities that now sports are using. And that's why we don't see stolen bases as much in baseball anymore. I love stolen bases attempts in baseball. We don't see those as much anymore. Why? Because the analytics tell us it's not worth giving up that out. So that's why you don't see most teams take the risk unless you have someone that's really good at stolen bases. That being said, since they're changing the rules of Major League Baseball, that the pitcher is now only allowed to throw at a base 2 times to try to get the speed of the game moving, I do think we'll start seeing more stolen bases because there'll be less risk by the base runner, which means they'll have to update their models.
There was one more
Sports and
question in
data
the
science
Q&A
is
about
fun.
just sports and data science, and I was trying to answer, but my chat is lagging. But I was like, yes, it's used a lot in sports. I'm sure that you have more data than I do on that, but I was like, Moneyball, that was what that movie was about, was how they were using
Yeah,
it.
so that was sabermetrics, and that was kind of like, as I said, another question, precursor to using data science properly. But yeah, now all the teams are doing sports analytics. They have maybe in another life or something. I mean, that'd be like an awesome job, right? I mean, you're paid by the Dodgers or whatever, and your job is to do data science for the Dodgers to help them win, and that would just be really cool. So yeah, every professional team has people that do that now on their payroll, or such positions didn't exist a few years ago. And it's not just sports teams that are doing it; it's of course other industry. And while they're doing it, it's not because baseball teams are a top 500 company wants to waste money. It's because they want that competitive edge, so they can make more money for themselves and their stockholders. So because of that, data science is an increasing important and growing field, because whatever it's called at a company, you need these technical skills, so you're able to manipulate and wrangle the data, so you're able to tell your boss, hey, this is what we should do and this is why. They're not going to care about the details of the model. They're not going to care about the details that even we went over today with the XG Boost, but they want to know, hey, what choice should I make? Should I do A or B? And you can say, well, the model tells me this is the model, this is what it tells me, I would suggest this. And they go, okay, cool. That's the actionable result they're looking for. Application biology, chemistry, and physics. That's another thing I'll write down. Even an old-fashioned piece of paper. I like being old-fashioned sometimes. I'll also add that to as an appendix or whatever to the blog. Python, and I probably should write down as well suggestions on that. Obviously, there's actually some O'Reilly books that are, I think, that are on that as well. But I think that's another one. Yeah, there are companies. Yeah, so there are companies that's their. I'm blanking on one of the big ones right now. But yeah, there are companies, and that's actually what their existence. They've actually always been stats companies for sports, but they've certainly changed with the times as well. Yeah, and so that sometimes you're right, the having that specialized knowledge is difficult, and that's when you're working with that road engineer, right? You're trying to use data science to get the lights to help with the flow of traffic, and you have the data science knowledge, but they have the knowledge about what can you actually do the lights, when are the roads going to be repaved so that there's still going to be a good flow of traffic, people are actually still going to be able to go from point A to point B. So it's not expected that you have all of that knowledge, but you need to be conversant enough with it. So when that expert who doesn't have the data analytics knowledge, that you guys could work together and figure out the best solution. So I will write that Python and bio and chem and physics. Okay.
Okay, well, if there aren't any further questions, we'll go ahead and oh, there we go. Okay, perfect. Thanks, Barbara. Thank you for everybody that joined into Zoom today, taking time out of your very, very busy schedule to come to one of our events. Always means a lot to us. Like I said, I dropped the link for the admissions questions if you have any questions directly about our data science program and would like to talk to somebody about it, as well as our YouTube channel. Thank you again to Brendan for all of your knowledge, and have a wonderful day. Bye, y'all.